Okay, we're going to be covering section 4.8, modeling real-world data with polynomial functions. We've done something very similar to this before. We modeled real-world data with a linear function, and that's the first one we have up here. We have linear y equals ax plus b, which is just a straight line. We definitely studied that before with best fit lines, linear regressions. Can be done either way. Very important concept for our state test, PSSA test. Guarantee you that there will be a question on the test dealing with linears. Okay, we've covered that before. But when you get into the higher level maths, linear is not enough. Sometimes you get data that acts like other things, looks differently. So we have to open up our arsenal to the other polynomials that we've been studying lately, and that's the quadratic, which we studied a lot. We pretty much solved quadratic every way that we could possibly do that. Quadratic is y equals ax squared plus bx plus c, and we know that it looks like a U or an arch here. Also, the cubic, y equals ax cubed plus bx squared plus cx plus d. We know that looks like a drain pipe. Okay, so if you forget that, go home, look under your sink, drain pipe. Quartic, y equals ax to the fourth plus bx cubed plus cx squared plus dx plus d. And that looks like an M or a W. In this case, it looks like a W. So if we see a set of data that's curving in different ways, we can now start looking into these different functions. And eventually, we'll get into logs, exponentials, logistics, and we'll even have more to use when we get to those. So that's what we're going to do. We're going to look at some patterns and see if we can match it up to one of these four possibilities, leaning more towards the latter three since we've already studied linears. Here is the first example. We have a set of data. We have an x and an f of x. F of x represents y. Our x values are -1, -0.5, 0, 1/2, 1, 1.5, 2, 2.5, 3, 3.5, and 4. The corresponding y values are -10, -6.4, -5, -5.1, -6, -6.9, -7, -5.6, -2, 4.6, and 15. I'll give you a couple seconds here to copy those down. Now, what we'd like to do here is we're going to write a polynomial function to model the set of data by using a graphing calculator. So we're going to come up with an equation. That's all we need to do here. So we have to use a graphing calculator. You have no choice in this unless you have a computer that has another type of program that will do that. I know Excel has, Microsoft Excel has some options there. I know you can definitely do linear regressions on there. I'm not sure how many others that you can do. There's a program or a district used also called Logger Pro, which I believe will also help out with this. But ideally, we'd like you to use a graphing calculator. So if you don't have one, on my website, you can download one. And let me show you that real quick. If we go to the Mount Pleasant website, here's my website, teacher website. And if we go to PreCalculus, there is right here download graphing calculator instructions, and it tells you exactly how to do that. The instructions will tell you what website to go to and how to download it. So please do that if you don't have a graphing calculator to use. Okay, so I'm going to pull up my calculator. This is the one that's on the computer, okay, and we're going to put the data into this. So let's scroll this data up a little bit so I can see it. Okay. We're going to go to Stat, and we're going to go to Edit. if there's any data in here, if you go up to the list and hit clear, not delete, clear, you can clear out a list. If you hit delete and the list goes away, go to stat and number 5 setup editor. Let me go ahead and do that for you. Let's go to stat edit. I'm going to delete the first list by accident. Okay, it's gone. Where'd it go? I don't know, it's gone. I go to stat, setup editor, number 5, hit enter. Once it says done, go stat edit, list 1 is back. Okay, I'm going to use list 1 and list 2. So typing in the data, -1, -0.5, 0, 1/2, 1, 1.5, 2, 2.5, 3, 3.5, 4. Again, we should probably scroll up through, making sure we did not mistype anything. Everything looks good. So we'll put in the second set, -10, -6.4, -5, -5.1, -6, -6.9, -7, -5.6, -2, 4.6, and 15. Again, if you wanted to, we can scroll back up through, just verifying that we did not mistype anything. Because if you mistype it, you're going to get it wrong. If you have the wrong data, it's very important you have the correct data. Everything looks good, so we're ready to find the equation. Stat, calc. We scroll down, we have some options here. Number 4 is linear regression. That's what we did before. Number 5 is quadratic. 6 is cubic. 7 is quartic. That's where we find them. It's probably a good idea to graph the data first to give you an idea of what curve it's going to look like. So let's go ahead and do that. We have the data in a stat. So we'll go to second, y equals, where our stat plot is. Choose number 1, turn it on. Okay, we want the first type. We want X list to be L1, Y list to be L2, and then your mark sheet would be the first or second. The third one's very difficult to see. I would not suggest that. Okay, so once you have that, we're going to go to Y equals. It's important you go to Y equals because if you use a calculator before, you might have something in there that you don't want in there. Right now we have no equations that we want to graph, so we want to clear anything out that's in there. Once you've done that, we're going to hit zoom. We're going to go down to number 9, zoom number 9, which is a zoom stat. And we get a nice curve. It's actually very nice. If you go back and look at our possibilities here, I think you can see that this curve matches up very nicely to the cubic. Okay, so it looks like a drain pipe. So we're going to go ahead and calculate. So we go stat, calc, cubic regression, number 6. Cubic. We're going to hit second number 1, so we want to specify our list, comma, second number 2, comma's right above number 7, and hit enter. And it tells us our A, B, C, and D, just as you see right here in our cubic. Okay, so we can write that down. One thing is missing, though. There's usually an R squared. An R squared is called the coefficient of determination. You hit second, 0, the catalog, and you scroll down to diagnostic on. Okay, diagnostic on. Choose diagnostic on and hit enter. When it says done, we're going to redo the stat. So stat, calc, number 6, cubic regression. If you look up in your calculator manual, if you have bought one, you do not have to specify list 1, list 2 like I just did. If you're using list 1 and list 2, the calculator always defaults to those 2 lists. So really the only time you need to put in list 1, list 2 is if you are using other lists. So I'm not even going to put it in this time. There it is, the R squared value. So let's go back to the page we were on. Let's write down the equation and the R squared value. So it's y equals 1x cubed, or we just write x cubed, minus 3.002x squared, plus 1.005x, minus 5.002. Our r squared value is, well, 1.000. That's pretty much perfect. And r squared, if you remember correct, r is called the correlation coefficient. And that is between -1 and 1. R squared, we call the coefficient of determination. Now, quadratic, cubic, quartic, none of those have an r. They all have r squares. So if you want to compare that with linear, you have to look at the r squared. R squared is between 0 and 1. Again, if you remember, 0, think of it as a percentage. 1 would be like 100%, 0 would be a 0%. So this is pretty much perfect. Again, we rounded that to 1.000. It's very close to 1, so it's very, very close to perfect. And that's all we had to do for that problem. Just find the equation. So we wrote a model. Let's take a look at another example. Okay, here we have years, and we have pounds of waste per person per day. I'm assuming that's garbage. So the amount of garbage someone would create in a day. So we have 1980, 85, 90, 91, 2, 3, 4, 5, 96, and then jumps to 2001. And then for pounds of waste, we have 3.7, 3.8, 4.5, 4.4, 4.5, 4.5, 4.5, 4.4, 4.3, 4.4. Seems to be pretty steady between 3.7 and 4.4. Part A, what polynomial function could be used for this model? Find the equation for that function. So basically, we're going to do pretty much the same thing we did in the last example. One thing I do want to caution you on, when you are using years, I highly suggest whatever your initial year is, you make that 0, or make something near it 0. That was instead of 1980, like 1982, I would still say that 1980 would be our starting point. Okay, you need to pick a starting point. And then, so this would be 5, 10, 11, 12, 13, 14, 15, 16, and then this would be 21. Makes a big difference in the numbers that you're going to get, especially when you start getting into exponentials, higher level polynomials. You could get errors because of how big the years would be. So break it down into time since a specific year. All right, so that's what we're going to put into our calculator. Okay, so we'll go back to the calculator in Stat, Edit. Now I'm going to clear out my lists. So I'm going to go L1 and hit Clear, not Delete. L2, Clear. Clears out everything that was in there. Okay, so put this data in. So I'm going to put in 0, 5, 10, 11, 12, 13, 14, 15, 16, and 21. Again, scroll back up through just to make sure we didn't mistype something. Looks good. Go to the second part. 3.7, 4.8, 4.5, 4.4, 4.5, 4.5, 4.4, 4.3, and 4.4. Okay, now that we have the data in, let's take a look at the graph, see if we can figure out what this might actually look like. So y equals is good, stat plot is on, still graphing 1 and 2. So if we hit zoom 9, we should get a graph. Not as pretty as the last one, that's for sure. So what could this model? I think this could be almost anything. This could be quadratic, could be cubic. Looks like it might be going back up. Could be a quartic. Well, I think we should start calculating some regressions here and see what's best. Okay. Stat. About stat calc. I'm going to start with linear regression. Just to show you that again. Linear regression. Again, if I'm using 1 and 2, I don't have to specify the lists. Okay, so we get an equation. What key is, we're looking right here at the r squared value. Okay, r squared is 0.58. That's about 58%. That's not real good. That means that it doesn't correlate very well to a line. So let's take a look at another one. Stat calc. Let's do quadratic this time. So we had 58%, 58.4% for linear. Let's do a quadratic. That's much better. We're all the way up to 82% now. 81.7%. So that's definitely a better fit. 81.7. Okay, let's try it a little bit higher. Stat calc. Let's try cubic. Number 6. 81.7. Now we're at 82.7. So that's a little bit better. Not much better. Just a tiny bit better. And the last one we're going to try is a quartic. Stat, calculate. Number 7, quartic. Okay. Notice that we have a down arrow. That means we're missing something. We don't see the r squared value. If we push down, there's the r squared value. That is much better than what we've had so far. 98.2%. That's the one we're going to use. So let's put this equation down. Let's scroll back up so I can see the whole thing. So we have y equals. Now we have to be careful about how we look at this data. Notice our first number says 1.1898484e. Well, what does that e stand for? That e stands for scientific notation. That's times 10 to the. That's what that e stands for in a graphing calculator. So times 10 to the negative 4 means that we have to move this decimal place 4 to the left. That means the number is smaller than what it really looks like. So to move this 4 to the left, that means we're going to move it 1 over and then 3 more zeros. So this is going to be 0.0001 x to the 4th. Now b doesn't have that, so we can just put that in there. So negative 0.005 x cubed. C doesn't have scientific notation. All right, we have plus 0.067x squared, negative 0.202 x, and 3.700 on the end. And the r squared value, again, if we scroll down, r squared equals 0.982, which is a very good number, 0.982%, 98.2%. Okay, so this is what we feel would best fit that. Again, this is a prediction. This is our best guess. Is this accurately going to predict the future? Nobody knows. Okay, anything can happen. Anything can change. Pounds of waste per person, the amount of garbage people use, that might drastically change to the point where we're not using too much, or it might go in the other direction where we're not recycling as much, and we're using a lot more. We're creating a lot more waste. Okay, so this is the best guess. One of the other models might actually be a better predictor. We won't know that till we get more data. Okay, but we made a best guess. This is what we think is going to work. That's the equation. So let's move on. That's part A. Let's look at part B. Use the model to predict the amount produced per day in 2010. Okay, bring the calculator back up. Now, 2010 is a year. That's our x values. 2010 is equivalent to 30 according to the numbers that I wrote. If 1980 is the 0, 2010 is 30. So that's what we're going to plug in. Now, to use the calculator, we need to put this equation into y equals. Now, you can type this in by hand, or the calculator will do it for you. Bars, right beside the clear button. Number 5, statistics. To the right, 2 to equation. The very first one says regression equation. That will give you the very last regression that you did. The last one that we did was the quartic. So we hit enter. It'll put all of that in. Not rounded exactly as we want it. The less rounded, the more accurate it will be. Now, if you have a TI-84 graphing calculator at home and you're doing this and you have the math print, the bars that we just did, bars, statistics, regression equation, we've had some difficulties pasting into y equals with the math print option. So my suggestion would go to mode. Now, this one doesn't have math print, but if you scroll all the way down to the bottom of your mode, eventually you should see math print in classic mode. Okay, it should say math print in classic. Pick the classic. Okay, the bars pasting of the regression equation works in classic mode. That's what this is. This is what you should see in classic mode. The math print mode, for some reason, there's difficulty in putting that equation in, dealing with the exponents. Okay, so please use classic mode so we can figure out that issue. Okay, once we have this in here, we're going to hit zoom 9 and see how this data fits. And it fits very well. Okay, so we want to predict at when x is 30. Second trace. We want an x value. Number 1, x equal to 30. And we get an error. That's good. That's okay. Error is not a bad thing. So let's quit. We're going to go to window. The reason why we're getting an error is because the x max is needs to be larger than the value we're trying to calculate. 30 is not between -2 and 23, so I'm going to make this say 50. That way we definitely know we have it. And then we hit graph now. Just hit graph. Calculate the value at 30. And there we go. Y equals 14.959. That's going to be pounds of waste per day. That's a lot. I hope it never gets that high. That means we're doing something wrong. You got 15 pounds of waste per person per day. That is a lot of waste. I hope our prediction equation is wrong. Okay, so we made a prediction for 2010. There's a part C. Use the model to predict when the amount of waste will drop to 3 pounds per day. Okay, well, 3 pounds per day. If we had 3 pounds per day, that means that we want to make y equals 3, because the pounds of waste is your y value. So to calculate that on the calculator, you simply go into y, go down to y2, and set y2 equal to 3. And wherever our graph hits 3 is where that would happen. I'm going to hit the window and make sure that we are able to see that. Right now we're not. I'm going to make my y min 0, the y max 4.5. That's fine. 4.636. So let's hit graph. Okay, there's my line at 3. Here's my line at 3. Okay, actually, let me change the window to 2. That way it's easier to see this. Right here's my line at 3. Here's my equation up here. Is our equation ever going to hit 3 pounds? The answer is no. Based off of our formula, our best guess, it will never get back to 3 pounds. So maybe our prediction's not that great, or maybe that's what's going to happen. Maybe the world will become just a bunch of landfills, because if we don't ever come back down or keep at least maintained at a certain level, and it skyrockets like our equation is predicting, we're going to be in some serious trouble. We'll be living around just a bunch of landfills. So let's take a look at a different model and see if we can get this to work. The one that I'm thinking of is the quadratic. So I'm going to write down the quadratic. I know that wasn't the best r squared value, but I think this is going to give us a little bit better results for this application. Okay, so here's our quadratic. R squared is, it's good, but it's not great. It's not as good as it could be. So let's go ahead and go into y equals. We're going to clear out our quartic. We're going to put in the cubic. Now, since that's the last one that is calculated, the bars, statistics, regression equation will work. There's the unrounded form. I still have my y2 equal to 3. So let's go ahead. I'm going to go back to the graph. Let's go ahead and start with, the graph I had should be fine. Okay, there we go. So you can see our quadratic, our parabolic curve. You can see y equals 3. Okay. So we should be able to calculate this now. We need to calculate the intersection of this curve and this line. So we're going to calculate the intersection. Second trace, number 5. We'll put the x as close as we can get to that intersection, hit enter 3 times, and we'll have our solution. Okay. End up with 36.617 years. From 1980. So that's going to be 2016. What day specifically? We can figure that out. 0.617 should give us an idea. There's 365 days times 0.617. 2016, day 225. That's about when we think that's going to happen. That's probably what, mid-July? Figure out what day exactly that would be if we wanted to. But day 225, sometime during that day, is when we predict that it will get back down to 3 using the quadratic model. Okay. And again, things that quadratic model might actually be better because when we apply maybe a new law, it says everybody has to recycle, so there won't be as much waste. Okay? There's a lot of things that can change that. So that's it for this lesson. You guys should now be able to do your homework.